any case, thank you very much. I changed a little bit my title because I thought, you know, when I heard some of the talks and looked at the program, maybe this focus is sort of more interesting. But I mean, what I originally wanted to talk about, sort of, I've reserved my last 10 minutes for that particular topic. I mean, so anybody who really was interested in that, I mean, will see a sort of very short summary. Okay, so this will be about Toda lattice. That's of course a well-known and very famous integrable system, and the whole talk will be essentially about Toda lattice. And let me sort of just, in order to start, let me sort of say a few words about its definition and some of its properties. So these are so if I think in terms of a fluid picture, I mean, these are particles which are moving on the real line, and here I put you know, the energy. I mean, so you have usually kinetic energy, and then you have a potential energy which only depends on the difference of nearest neighbor in terms of labeling. I mean, the actual positions. So here's my X space. I mean, there's no ordering. I mean, the QJ, I mean, the position QJ of the chase particle is completely arbitrary, and the particles are not ordered in any way. Okay. So we can look at various things. I mean, at the moment, because I want to think about scattering, I'm thinking more about the open system. So these particles, these end particles, are just moving on the infinitely extended line. But we can also think about a ring, which is sort of usually called the closed system. Okay, so that's fine. And now another way to look at this problem is to think of this. I mean, this is sort of more like the original Toda picture, that he was thinking more like a discrete wave equation. And of course, you know, it's the same thing. It's just sort of somewhat different way of looking at the same system. In this case, you think there's sort of an underlying lattice, which of course, you know, the label of this lattice is just sort of the index of the particle. So this would go from 1 up to n. And then it's very common to introduce these flashcard variables, which are, you know, analytically very useful. I mean, you do some of the physical intuition, but, you know, it's a beautiful and very powerful mathematical tool. And so, you know, they're quite simply defined. I mean, first of all, you just keep the momenta, which are called p sub j here. And the new variables, you first sort of define the free volume, which is the difference between qj plus 1 and qj. And this can have any sign. But then you take the exponential, and the 2 comes because essentially you want to take the square root of the interaction. And so you take hj as rj over 2, and then you write down the equations of motion. That's a simple transformation. And you see that sort of, you know, they have a very different appearance from Newton's equation of motion up here. They are now quadratic, and you have sort of coupling of your variables to the right and to the left. Of course, I have to supply this with boundary conditions. I mean, for the open chain, in this, you know, for that particular case with n particles, it would mean that I would have to put the A0 equal to 0 and the AN also equal to 0. And then, you know, sort of the big discovery in the mid-70s is that this system has a Lax matrix, which is sort of the starting point of the analysis. And in this case, it's very simply defined. It's just a triangle matrix. I put the n momenta I put on the diagonal. I mean, see, these are the PJs. And then on the off diagonal, I put these flashcard variables, which have indices by these boundary conditions, which go only from 1 up to n minus 1. And that's my tridiagonal matrix. And, you know, this sort of looks about at that moment sort of, you know, so unmotivated. But the main point about the Lax matrix is that when I look at its time derivative, you know, the Lax matrix evolving under Newton's equation of motion belonging to the Toda lattice, then you see that it can be written in terms of a commutator with some other matrix, which I'm not even writing down, which I, according to Toda, I mean, likes to call it P sub n. Okay, so this system, of course, you can look, I mean, like for here, for the fluid, you can think having sort of infinitely many particles moving on the real line, but also for the lattice, I mean, you can sort of let n go to infinity, and then typically you sort of get a field here which lives on the one-dimensional lattice. And which I'm not going to tell in formulas, but I guess in this audience, I mean, sort of people know what I'm talking about. The Toda lattice also allows for an inverse scattering transform. Okay, so that's my basic model, which I'm going to study. And next, I want to show you a picture. So these are, so here is time, and axis goes upwards, and here it's just a numerical simulation of 16 Toda particles. here are sort of, you know, randomly picked initial conditions, and then you just solve Newton's equation of motion. Now, what I want to, there are several reasons why I want to show you this picture. I mean, the first thing is that, you know, if you wait long enough, you somehow, if you start with random initial data, with a smooth density, then somehow you could imagine that, you know, things are mixing up and eventually you will reach a stationary situation. That's actually a mathematical theorem. I mean, this was proved by Kappeler, who sort of showed that, you know, one really has action angle variables, and you have this motion on the tori, and the energy, I mean, the Hamiltonian expressed in action variables is actually a convex function and has no flat pieces. And then it's sort of a general theorem that such kind of things actually approach a long time limit. So that's one thing. The second thing I wanted to explain is that later on I will look at scattering situation. You know, then you just have to remove these lines. Here I use periodic boundary conditions. Just imagine that I remove them. Then of course, if I wait very long in the future, eventually, because, you know, the potential is repulsive, particle will separate and eventually will be sort of, you know, I mean, very far apart and will just move like free particles. And of course, the same thing will happen in the very past. And the third thing which I want to emphasize, because that's sort of connected to this hydrodynamic limit, is that, you know, when you look at these things, I mean, for instance, here you have sort of a collision where you know, particles sort of crosses actually are then across each other for a short while, and then they sort of separate again. I mean, you have more normal collisions, I mean, maybe like this one. Now you see it's a mess. I mean, you know, the idea that you could understand the dynamics of the system in terms of these sort of two-body collisions, I mean, that sort of looks pretty sort of, you know, a long way to go, but it's amazing. I mean, this integrable system, and you see, for hydrodynamics, we really would like to have theorems which are not only sort of, you know, try to understand behavior, which does not only refer to very low density, but we really want to look at very dense systems, and the Toda system can be extremely dense. I mean, at the particular parameters, I mean, you know, it will be sort of, you know, barely extensive. And therefore, this is one of these riddles, and sort of I'm trying to sort of explain you know, at least sort of in the case of the Toda lattice, I mean, you know, one can solve and see that despite the fact that you cannot, you know, separate things into sort of pair collisions, when you look at hydrodynamics at the end of the day, I mean, it's only the pair collision which are the two particle scattering shift more properly, which enters into the picture. Okay, so that should sort of give you a rough idea. And now let's see what I put here as my next what's happening here. Okay, that's my next slide. Okay, so now comes sort of this idea of the two hydrodynamic scales. And one thing which you can do, and which is sort of, you know, I mean, people who sort of come from KDB is sort of the most natural thing they would do immediately. They say, well, I mean, why don't we look at the soliton gas? I mean, so that's a gas which sort of corresponds of, you know, objects which I have not yet defined, but I just sort of remind you of the one soliton solution. This was sort of, you know, the first breakthrough of Toda, that he could actually find that particular solution on a discrete wave equation. And you know, the solution, I just write it down. So for completeness, I mean, you know, it's asymptotically one. I mean, that's sort of the background. And then you sort of see sort of a peak, which sort of, you know, is well localized. It's a sort of 1 over cos squared. So, you know, it's a function which decays exponentially, and it sort of propagates linearly through the system. There is the omega in front of the t. I mean, that happens to be sinh eta. I didn't tell you what is the eta parameter. The eta parameter is what people call the spectral parameter. And that's related to the fact that you have this inverse scattering transform. And then there's an operator appearing there, and it's, you know, its eigenvalue sort of determine actually this particular solution, and therefore this quantity is called spectral parameter, which in our case is just a real number, and that's sort of simply the form of the one soliton solution. And so you see, because I put the eta absolute value outside, I mean, it has a velocity which goes like sinh. I mean, that's this term divided by eta absolute value. And when you sort of look at, you know, how the velocity depends on this spectral parameter, then you see that there's a gap between -1 and 1, and then it starts sort of quadratically, and then eventually increases exponentially. And then, of course, there's another important parameter, which is the shift. I mean, of course, you know, this soliton can sort of live everywhere on the lattice, and therefore, you know, another parameter of the soliton. So one of them is the eta, which is sort of like a parameter which sort of rules the velocity, and then there's simply the spatial shift, which is this delta. Okay. Now, once you have a single soliton solution, you can sort of work harder and actually do a 2 soliton solution, which again I'm not going to write down. You know, these are formulas which, for what I'm doing, sort of are not very relevant. They were obtained a long time ago, but still for completeness, and so you can see that they are actually very concrete formulas. I want to show you, I mean, that the 2 soliton solution has now sort of, you know, 2 parameters, because each soliton can have its own spectral parameter, so to speak, and it has 2 shifts. And so altogether you need sort of 4 parameters to characterize the 2 soliton solution. And what is sort of interest is actually the long time behavior. And so here I've plotted the picture down here. I mean, you see that here maybe you have soliton 1 and soliton 2, and they are moving sort of essentially along straight lines with their own velocity. But then, you know, there's this complicated interaction region. And of course, you know, during that region, it's just like for the Toda particles. I mean, you don't know which is which, but eventually they separate, and they separate again exactly with the same incoming, you know, to the same velocity as the incoming velocity. But on top of this, there is a shift. And since we work here with 2 particles, well, it's called the scattering shift, or it's also 2 particle scattering shift. Okay, so that's just the shift which these solitons achieve asymptotically. And you see for Toda it's already slightly more complicated. You have to distinguish whether this product happens to be positive, which people call sort of like an overtake collision, or a head-on collision where this product has to be negative. Okay, that's fine. And of course you can do the n-soliton solution. I mean, Benjamin in his talk, I mean, he showed you already that, you know, you have now in the far future, you have sort of solitons coming in, then there's sort of a region where there's a lot of mass and you cannot really distinguish. But if you wait long enough, I mean, they come out, and eventually sort of will be characterized, you know, according to the incoming velocities and the corresponding scattering shifts. Now, the amazing point about amazing, it shouldn't do. I mean, it's a long time ago, but it's still sort of a surprising point when you sort of read about it. First is that you know, you might imagine that these scattering shifts are sort of something very complicated, but no. I mean, despite the fact that things are very messy inside, eventually, you know, they can be expressed. I put here the sign sum because you have to sort of, you know, look whether it's from the right or left, but in any case, it's a sign sum. I mean, there are plus and minus signs of the 2 particle shifts. So this asymptotic behavior can be understood once you have the 2 particle scattering shift. And then there's a theorem, which I don't know, I guess Tanaka, or I mean, anyway, so this theorem, which was proved a long time ago, is that if you do this sort of for the n-soliton solution, well, okay, maybe it was, never mind. I mean, so anyway, I mean, you can prove that when you have the n-soliton solution, you look as an tossing behavior, it will be sort of do exactly what I'm just telling you here. You can also look at general initial data. I mean, this is work by Teschel. I mean, you basically assume that you have some decay. I mean, so you see that the HA, you know, is asymptotically 1, and you want to have sort of this first moment to be finite, and the PJ squared, you also want to have the first moment to be finite. So in some sense, it's sort of initially localized initial data. And then what he proves is that when you look either at t going to plus minus infinity, you will see an n-soliton. So you will see a behavior sort of something like this, sort of n-solitons well separated from each other. But then there's still a rest, I mean, which people call radiation, and this radiation sort of decays with the power law and sort of in the long time limit somehow disappears. But the point is that you know, I say here you find an n-soliton solution, but at least to my knowledge, I mean, there's no sort of simple scheme than just looking by the initial data, you know, to determine even n. I mean, the n of course depends on initial data, but which n you get, you know, it's something which I don't think is really understood in terms of you know, just looking at the initial data. Okay, this point will come up. I mean, so but sort of, you know, as a qualitative behavior, I mean, you have this kind of information available. Well, now let's look at the particles. I mean, so you can do also particle-based scattering theory, right? I mean, it's just sort of like you would see sort of you know, if you come more from, rather than coming from the sort of, you know, hallways of KdV, you come from the hallways of classical mechanics. I mean, it would be this scattering theory which you would look at. And in this case, it's sort of the Lex matrix, which helps you a lot. Namely, if I look at the eigenvalues of the Lax matrix, these are conserved quantities, they will determine what are the asymptotic velocities. And therefore, if I look at the position of the chase Toda particle at time t, then asymptotically will move linearly with one of the eigenvalues. And then there will be this shift, which I call here for the future, that will be the phi plus j. This happens for t going to plus infinity. And you, of course, have similar behavior for minus infinity. But remember that, you know, in the previous picture, maybe I can show you here in this picture, you see this one will go here. I mean, so this is why I have to put here at j plus 1 and also times t. And then there will be a shift at minus infinity. But then the scattering shift is actually something which is determined. So the difference of these two things are given in terms of the scattering shift, and of course it will be the sine sum of the two particle shift, of the two particle scattering shift. Okay, and so you see that again, you have sort of like two n parameters which characterize your solution asymptotically. You have n eigenvalues of the Lax matrix, and you have, you know, here there are two n parameters, but the scattering shift fixes one of them, and therefore you have n shift parameters. Okay. Now, and for the Toda lattice, I mean, you know, if you look at this thing, then computing the two particle scattering shift is very easy, because you just have to look at the motion of two particles, which is sort of a standard problem which you give to your students, and you know, you can work out the explicit solution. And in this particular case, you find that the t, okay, so that the scattering shift is 2 times log times the difference of the incoming velocities of your particles. So the lambdas, let's say, I mean, that's a WM prime. Now, since, oops, this was not so good. Very good. I'm sorry. Okay, so since the scattering shift, you know, will come up more quite often, and I guess Benjamin used a slightly different notation. He used the phi for this symbol. So I'm using here t, and then I use a capital T because, you know, very soon, I mean, this will be the kernel of an integral operator, and it's sort of very convenient to have this WT. I used already this notation before for the soliton two particle scattering shift, and here sort of I didn't emphasize this point. And you see from this picture, I mean, from this formula, I mean, you see that this kernel can have positive and negative values. So I have the same convention as Benjamin. For small v, as for small w, it will be actually, or small w differences will be actually negative. This corresponds to sort of like collisions like you would have for hard watts, but then it can be also have negative, you can have positive scattering shift, and then you will see that, you know, the two particles cross and then sort of separate again. Okay. Now the conclusion of this introduction is that you see, you have two types of scattering theory. Therefore, I can do hydrodynamics based on solitons, and I can do hydrodynamics based on particles. So, you know, I remember that I was sort of telling these people at the MSRI, which are people who are coming more from the KDV side, and I said, look, I mean, for the Toda lattice, the particles are the solitons, and they were completely shocked. I mean, they want me to sort of essentially throw out of the institute, but it's completely correct. I mean, the point is, you know, one should not use the language because it's too confusing, but one should remember that once I look at solitons and once I look at particles in terms of scattering theory, you will see no difference qualitatively. It's just a different scattering shift. Okay, so now let's see what we can do. Yeah, so now we do this soliton-based hydrodynamics. Since Benjamin sort of explained this, as now I can be sort of, you know, rather brief on this. So first of all, you have to introduce the soliton counting function, which is a little bit mysterious object. But the way how you naturally define it is sort of what actually people do in the experiments, which is this time of flight method. I mean, you know, here's a small volume, and then you want to ask yourself, what is the value of this object? Well, I mean, you know, maybe in this volume you have sort of like 5,000 particles. I mean, you just look at this particular configuration, and then you let them just evolve. I mean, you let the solitons, I mean, you let this sort of soliton type of configuration evolve, and then, you know, they separate, and then, of course, you can see which kind of solitons are actually in this little volume. I mean, for the particles, I mean, there's a more elegant method, but here I don't think what else one can do. In any case, I mean, so here I've written down this standard hydrodynamic equation, which you have seen already with an effective velocity. And as Benjamin emphasized, I mean, the V effective is a nonlinear function for fixed x and t. It's a nonlinear functional of the f. Okay, and then of course you want to know what this effective is, and you write down this collision rate ansatz, which is exactly in the way how you have seen it already. And sort of the philosophy behind this is that you have sort of a tracer, a quasi-particle which moves with a bare velocity, and then it's sort of corrected by collisions. Now, the thing which I want to point out is that you can sort of solve this equation. I mean, you know, the solution doesn't mean that it helps very much, but I just want to point out that you know, there's somehow a formalism which you can numerically implement, and which you have to do whenever you want to compare, you know, the solutions of the you know, whenever you do sort of numerical solutions of this hydrodynamic equation. And here in our case, the in quote solution is that you define a new quantity, which is a rho sub n, sort of a number density, which is simply defined by this thing. This is pointwise, so it's the operator t acting on the function f, okay? And then you define a tracing of a function, which is a similar type of, so here, just pointwise, here you have to do an inverse of an operator, which is sort of, you know, might create problems, but in any case, that's how way you do it. So it's 1/1 minus c rho n, and this defines, given psi, it defines the trace function. And once you do this notation, you get a somewhat different and less intuitive formula for the V effective. Namely, what you have to do is you have to take this function and trace it and divide it by this function and trace it. And the rho n has another beautiful advantage, namely it sort of automatically puts the hydrodynamic equation in normal form, which means that the V effective is sort of pushed outside the difference, this spatial derivative, and somehow to my feeling, I mean, this is somewhat the simpler equation than this one, and maybe deriving this one is easier than this one, but in any case, I mean, that's something for people who want to derive this equation. Okay, fine, and then now we just do exactly the same for the Toda particles. So now it's particle-based hydrodynamics, and you see that the only thing which is changing is that I use a different notation for the rho p. Now the rho p has now a sort of, in some sense, more direct meaning, because, you know, I can tell you exactly what I mean by this rho as a function of w. I mean, what I have to do is I have 1,000 particles, and now I want to ask myself, you know, what is this rho p function? Well, the prescription in this case is sort of fairly, you know, at least sort of algebraically sort of very simple. I just look at this configuration of 1,000 particles. I forget about the rest. I form my 1,000 by 1,000 Lax matrix. I compute its eigenvalues, and I compute what people call the density of states. I mean, that's just the density of the eigenvalues normalized to 1. And that's what is the correct sort of object for the rho p. And again, the assertion is that you have an effective velocity, which is sort of constructed according to this thing. Here, the bare velocity is w, because these are free particles. And of course, here you have sort of now the scattering kernel, which the two particle scattering shift, which comes from the particle Toda, from the Toda particles, not the Toda solitons. And then you have similar formulas, and of course you have, you know, this equation as hydrodynamic equation, and also the normal form. And so the simple observation is that you have two different scales on which you see hydrodynamics. I mean, they have the same structure, but they are different because the two particle scattering shift is different, but it's the same model. And now you might say, how come in the same model I have two different hydrodynamics? Well, you know, the resolution is sort of the obvious one. I mean, you're just looking at very, very different initial conditions. You see, I mean, the initial conditions which I would look in the particle-based hydrodynamics are essentially orthogonal, you know, have zero weight according to the initial conditions which I look for the solitons, and therefore, you know, there's no contradiction. I just have sort of two classes of initial conditions which have both, you know, proper hydrodynamics, but this hydrodynamics has the same structure because it's an integrable system. But you know, the equation, of course, are different. Okay, now having said this, I mean, we can maybe sort of rest a little bit and ask ourselves, you know, what about other systems? And so here I make comparison. Comparison, it just means I'm looking at this integrable system in terms of generalized hydrodynamics. I mean, you know, it's not a review of everything what has been written on this. I mean, this would take us too much time. So for the hard bots, it's obvious particle-based hydrodynamics. And for the box ball, it's obviously soliton based, right? I mean, there's no object which I could identify as a particle in box ball. And similarly, you know, there are no soliton solutions of the hard bots. Now for the KdV, it's obvious, you know, you have inverse scattering transform is obviously soliton based. For the Toda, I just told you that I have both, and you know, I have this inverse scattering transform to do this thing. I mean, this hasn't been done so much because, you know, KdV and other models and the nonlinear Schrödinger equation were somehow more important, and therefore, you know, this has not been analyzed. But in principle, I'm sure it could be done. This can be handled by a scattering method, on which I will maybe say one word. I mean, but it can also be handled by random matrix theory. I mean, so there are two which are give the same result, but are two very distinct problems. Random matrix theory refers to the fact that the Lax matrix under the GGE is a random matrix, and therefore you might hope that, you know, if you have some good methods from random matrix theory, you might hope that this sort of helps you to get at least some information about the Toda. Okay, then there's the Carloccio 1/sinh squared. That's an interesting question. I mean, I have not found in the literature any kind of soliton solution of this particle system. So these are particles with in one dimension with mutual interaction and with a repulsive potential like 1/sinh squared. Somehow you would think there should be, because it's similar to the Toda, but I couldn't find it in the literature. And this, I couldn't also find any connection to random matrix here, but this is a beautiful system which can be, you know, at least sort of the generalized free energy and other things can be actually computed via scattering theory. And LS, well, the answer is obvious. I mean, it's only soliton. Now there's the Ablovitz-Ladek, which me and other people, I mean, Tamara Grava and Guido Masuko, they studied. I mean, we use the particle system. I mean, of course, there's also the inverse scattering transform. So this too has to be done. I mean, but presumably can be done. I mean, but you have the tools. But one which is very surprising, I don't have any answer, is that I can do it only via random matrix theory. I tried hard to find what are the particles in the Ablovitz-Ladek. Ablovitz-Ladek is sort of a discrete version of the nonlinear Schrödinger equation. So it's sort of a lattice version of the nonlinear Schrödinger equation. I couldn't find it. I mean, actually, I really would like to know. I mean, somehow it must be somewhere, and that, you know, these particles should be objects which sort of have a scattering theory, as I explained for the Toda particles. Now I look at the integrable quantum systems, and I want to emphasize that all integral quantum systems are particle-based. And the reason why I can say this with such a confidence is that when you look at what enters into the hydrodynamic equations, it's the two-particle scattering shift and nothing else. And so that's, you know, what defines more or less sort of this whole column. And the reason is that, you know, quantum systems have, I mean, it's a sort of more complicated wave equation, and they have sort of a particle number conservation. And so when you compute the two-particle scattering shift for the quantum mechanical model, you solve a wave equation in a space of 2 dimensions, because it's two particle. Whereas if you want to know what is the scattering shift of the Toda, or if you want to know it about, let's say, KdV, then you have a wave equation in 1 dimension, and you want to see how 2 solitons are scattering, and these are 2 very different things. Now let's see. So now I want to go back to Toda, and yeah, I want to sort of make sort of a few remarks on you know, sort of the kind of things which I see as similarity and which I see as difference between sort of Toda and well, the 2 sectors of Toda, if you want some. Okay, so the one sector is sort of this issue of local stationarity and then generalized thermodynamics. So you want to have states, you know, out of which you can build your hydrodynamics. And the other one, which I want to briefly mention, is you know, this famous collision rate ansatz. Okay. Now I just want to say that, you know, the soliton based goes back to sort of pioneering work of Gennady L. I mean, this was sort of 2005. There was KdV and the particle based advances, you know, sort of computing this effective velocity. I mean, Benjamin mentioned already, there were these 2 teams which sort of, you know, made the important step in 2016. So let me first sort of say a few words about local stationarity and generalized hydrodynamics for the soliton. I mean, this is, you know, I'm not an expert on this, and I will say very little. I mean, so in this case, you know, the n soliton solution is actually a solution on the ring And then you have to take a limit, and this is sort of rather complicated. And maybe I don't want to go into. I mean, there's something called rhythm modulation theory, and there's band. You have to look at periodic Schrödinger operators and band spectrum. Anyway, what they say at the end of the day is that when you look locally, you should see an n soliton solution where the shifts are actually Poisson distributed with a particular density, and the spectral parameter is IID and has a distribution given in terms of the counting function. So it's just like what you would expect from kinetics theory. Okay? This is sort of what seems to be the consensus. I put here ideal Sierski. I mean, I put here pressure. I mean, well, okay, maybe I should not go into the question mark. All what I want to say is that once you look at this generalized, even the generalized thermodynamics, many things which are used from ordinary sort of, the usual thermal case can be different. I mean, the pressure is sort of one example. So I just want to say that one has to pay a little bit attention of how to extend this to sort of many conserved charges. Okay, so one thing about the one sort of big advantage of the particle-based hydrodynamics is that you get for free stationary measures and you get for free the conservation law. So here I just want to show you this for the Toda. I mean, so this is a generalized Gibbs ensemble, but the point is that so you have seen sort of more or less the formulas already, but you see, I mean, you get this conservation laws. I mean, if I look at the conserved fields, then for every configuration, I know what I mean by the density of the conserved charges. That's just this expression. Of course, it's written in terms of the Lax matrix. And I should have put sort of, the capital N, I'm thinking of N particles here, but I left it out sort of for E. And then so you see this density, and you take its integral. So when you integral, then you get just the trace, because you have to sum over J, you get the trace of Ln. And of course, since this is the Lax matrix, Ln is conserved. So you see that when I take the integral, it's conserved. And of course, these things sort of satisfies automatically the conservation. Or maybe I'm saying a little bit more about this later on. Anyway, I mean, the main point of starting with these generalized Gibbs ensembles is that you get actually a free energy functional. And that's something which, at least when I look at the solid tone, this work on solid tone based hydrodynamics, I mean, then I just never can find that. I mean, it's somehow not clear, I mean, but for the particle based, I mean, this is sort of a very crucial information. And I just written you, the free energy functional, which you get at the end of the day. I mean, here out in sort of in full length. And when you now want to know, so when you now want to, so V is sort of the object which characterizes the generalized Gibbs ensemble. So that's just a function which sort of grows at infinity. I mean, maybe quadratic or linearly, but otherwise it's a rather general function. And when I minimize this object, I mean, then you will get the density of states is sort of exactly, the asymptotic density of states. I mean, the non-random density of states can be actually obtained as minimizer of this variational function. And the fact that you have a variational function, sort of, tells you that you have a lot of identities which without having this free energy function in the back of your mind, I mean, you would hardly be able to discover. I mean, so you have to minimize under the second important parameter of this generalized Gibbs ensemble for fluids, which is simply the fluid density. So the integral over this particle over this rho p must be the fluid density, and you minimize, and then you have here a full function. So it's a full function which characterizes the generalized Gibbs ensemble, and it comes in this sort of rather simple way into this free energy function. Now, one way to actually derive this formula, so this is something which Benjamin mentioned in his talk, but he wanted to sort of put particles at time t equals 0 sort of in a box. I mean, this is a way which I mean, it's certainly correct, but the details might be not so obvious. I mean, what I discovered sort of like early this year is that you can actually put your Gibbs states in a carefully designed box potential. So you just confine it by a box potential, which has sort of this simple, sort of sum of two exponentials, which with the box size L or 2L, which sort of, confines the particle. And once you do this, I mean, then you can see that this very particular box potential transforms very simply into scattering coordinates. And once you have done this transformation to scattering coordinates, you can integrate out over the scattering shifts, and you find an explicit formula for the joint distribution of all the eigenvalues of the Lexford matrix. That is no n going to infinity. I mean, it's a formula which is true for any n. Once you have, such a sort of, in quote, informative information about the eigenvalues, then from there on, seeing that this is sort of the large n and L limit is sort of, I mean, it has to be done, but it's something which is fairly transparent. Okay, so this is what I wanted to say about this part here. And now the second thing which I wanted to, here comes the conservation law. What I wanted to explain to you is how can I avoid going through this beautiful collision rate ansatz. And then, the Toda lattice is a beautiful example for this. So this is based on this paper with Takato Yoshimura. And so the next thing, what since you know what the conserved fields are, you can write down what are the currents, right? I mean, so here I've written down the currents. I mean, the PJ comes from differentiating, first the delta function. That's now the currents of the n's conserved, but then you have to also differentiate this. And if you do this as a sort of slightly more complicated expression, this is just the ordinary step function, and here it's the Ln. I mean, there's always the index n here, capital N, but it's the nth power of the Lax matrix. And then it's sort of, the lower triangular part of the Lax matrix. And so if you take this now, you get an explicit expression for the current. And you see that's of the big advantage. I mean, now you can write down the conservation law, which is not something which is asymptotic, but, which is true for any configuration. That's what I wanted to emphasize before. Okay, but now you want to compute the GGE average currents. And now you see, in some sense, it's a sort of, a straightforward mathematical problem. I mean, you have here, I mean, you want to do the total current. I mean, so, you can put the x equal to 0 and you let the volume go into infinity, and then you want to just compute, this average value in GG. I mean, that's sort of, it's just, it's just a straightforward problem, but it looks very difficult. I mean, for a long time I had no idea how to do this very directly. And now the nice observation is that symmetry, which Benjamin also mentioned already, you use the fact that there's a symmetry of this charge current correlator. So let me just go through this a little bit more slowly. So now we are just in equilibrium. No, we are just in a GGE, in a generalized Gibbs state, and here this just means that I have to do the truncated expectation because I want to do an integral over the whole space, and therefore, general this will not decay to 0, so I have to truncate. And so here, these are these functions which I've written up here, and this is at point x, and this is at 0, and then I have to integrate that, and this sort of I can do here different indices, and that defines the matrix which I call here BMN. And the point is that as a very general fact, I mean, it has nothing to do with Toda. I mean, it's true for essentially any model which you can sort of think of, is that this matrix actually happens to be symmetric. I mean, this I knew a long time, but I didn't realize how useful this thing could be. And so now here comes the simple argument how you can avoid the collision rate. I mean, so I want to compute the average current number n, average in this Gibbs set, okay? And now I differentiate with respect to the chemical potential. And so this will stay, but what I will get down here, the 0 is conserved field. I mean, that's the density, okay? So it's just the usual, usual thing when you have Gibbs measures, when you differentiate, I mean, you get a correlation function. And the first factor is the current Jn, and the second factor is simply, the lowest order field, which has the label 0. That's how I pick the mu. But now this is a symmetric matrix, so I can also write 0n. Now n is now simply the n's conserved field, the n's charge, but 0 is now the 0 current. But you see, the 0 current is the current corresponding to the density. But the current to the density is the momentum. I mean, that's just a general fact about mechanical system. And so I know that the J0 is Q1. So you see that what I get is now a correlator of something, which sort of it's a correlator of eigenvalues, because these things are sort of, I mean, when you write it out properly, you see that these are basically sort of fluctuations or covariances of eigenvalues. And since I have an explicit formula for the eigenvalues, I can actually figure out, I mean, what this covariance would be. So now I'm not going to tell you detail. There's also this derivative you have to worry about, etc. But anyway, when you sort of complete this analysis, what you find is that if I use this very formula, then you find that, doing a little bit more manipulation, you find that the average current is given exactly by this formula here. And so, and this is true for any generalized Gibbs. There's no assumption on two particle collision or anything of that type. But and I get, of course, exactly the formula which everybody would expect. So this is an argument which I like, because very explicitly, it's, first of all, it's simple, and second, it's clear that I don't have to make any assumptions on the particular parameters, and therefore sort of explains to some extent why generalized hydrodynamics is expected to work also for very dense fluids. Okay, and this method actually works in general. I mean, at least in general, the model which we looked at, but there's one exception which is simply standing there. I just mentioned this as an open problem. When you look at the Fermi-Hubbard model spin 1/2 on the lattice, which is an integrable quantum model, then there is simply there's no such identity. I mean, there's no current which is actually itself conserved, and so there you have to rely on other methods. You cannot do it in this way. Okay, so now let's see what I have to say next. Okay. So now I want to So this is sort of more or less what I was trying to say about these two scales of two hydrodynamic scales of the Toda lattice. I still find it a little bit surprising that in one model, I mean, you can look at these two very different scales. And I sort of wanted to emphasize that our mathematical technology, which we have in the case of the soliton-based generalized hydrodynamics and of the particle-based generalized hydrodynamics, is very different. I mean, it's not, it's only at the end of the day you see that the things, behave so similar. I mean, but the way how we prove it, I mean, for the particles, I use sort of special properties for particles, and for the other case, I mean, the soliton-based, I mean, you have to dug more deeply into this inverse scattering transform, or anyway. So maybe at some point, these methods also become a little bit more unified. I mean, like scattering theory somehow looks like a tool which should be very useful in either case, but that's not where we are. Okay, so now I want to use sort of the last few minutes of this talk, I mean, to something which I want to tell you in much more detail, but still there's sort of one punchline which I would like to get across, and so you should not be worried too much about this formula. So this is sort of recent work with Tamara Grauer, with Thomas Gricherbauer, Ken McLaughlin, and Trudeau Masuko, and Christian Mendel. And what we looked at is just thermal equilibrium. So this is now the Toda at thermal equilibrium, which is certainly a generalized Gibbs state. The Lax matrix is particularly simple because the diagonal is just IID, and they are Gaussian, which is here see Maxwellian distribution. And of course, also the off-diagonal are IID, and it's very, if you do the simple transformation, you see that it's the chi distribution. This is sort of called the chi distribution. This has a parameter beta, which is the inverse temperature, and this has a parameter which is the pressure, which you see because here's a -1. In order for this to make integrable, the pressure should be strictly positive. Okay, so the Lax matrix is a very simple matrix, and of course, these kind of measures, for the infinite system, they are space-time stationary. I mean, obviously here, by this construction, but when you look at this thing, I mean, you also find that it's stationary in time, and so this is sort of a perfect GG and sort of a perfect thing which we can use for generalized hydrodynamics. But now I want to sort of do something which is sort of just a very small deviation from equilibrium. Namely, I wanted to look at the correlations of the conserved quantities in the thermal state. So that's why I put here beta. And here you see again, I mean, that's the conserved quantity at lattice point J at time t, and this is the nth conserved quantity at the origin at time t equals 0. Okay, and then I have to truncate. And this quantity I denote by a correlator, which is S, and it's sort of an infinite dimension matrix because M and N can go from 0 up to all the way to infinity. I mean, this is already infinite volume, so I have left the finite volume behind. And so, you know, you expect that if time is not too short, and then your positions are sort of not too small. So if you go to sort of ballistic scaling, you expect that you know, this thing has to be of ballistic form. And the 1 over t in front comes simply because, you know, when you do the sum over j, then you see that the time drops out. And so, you know, the same property you must have here. So if I do the sum over j, I mean, then, you know, this must be something which is independent of time. Okay. So now what we did, I mean, this is sort of what we started, you know, back at the MSI, but, you know, the things sort of progress slowly, but we are now close to a paper, is that we said, okay, you know, that's one of the beautiful things about you know, the Toda lattice and other classical system, that you can do very precise molecular dynamics. I mean, and of course you have to make some efforts, but you know, these are the systems where, you know, if you want to sort of, if you doubt about, you know, the theory, I mean, that's the one which you should use in order to check the theory. And in our case, I mean, so we decided to have, so this is mostly Chuido and Thomas Recherbauer who did that work. I mean, so we decided on 4,000 particles, and we looked at times which are 150 and 600. At 150, this ballistic scaling is not quite so good, but at 600, it's pretty good. You have to do a lot of averaging because data are noisy, so you have to sort of like 500,000 samples. So that's a typical order we have to sample. And of course, you have two parameters, so you have to think a little bit. Anyway, so I want to show you, we have many more things, which of course I don't want to show you, but we put the inverse temperature to 1/2, and the pressure has sort of 3 values. This is sort of, I mean, not really very low pressure, but sort of reasonably low pressure. I mean, that's sort of more like what I showed you in the first few graph. 0.95 is sort of maximal density. I mean, particles are really packed very hard. And this is even higher pressure. There, you know, you force the particles to anti-order. I mean, here the particles are ordered 1, 2, 3, 4, 5, and here they're just, you know, sort of ordered inversely. I mean, 5, 4, 3, 1, 2, 1. Okay. Now the main point is that these kind of things you can, I mean, Benjamin mentioned this already. I mean, this you can sort of actually compare, provided you find you know, the solution of linearized generalized hydrodynamics. Okay, so in our case we just looked at the more physical fields, m equal 1, 0, 1, 2, 0, 1, 2. I mean, that's momentum and energy, and so, you know, this is a particular object. This is a linearized hydrodynamic equation. This is a particular object which you have to do numerically, and for this you have to sort of use this TBA formalism. And so you have to invert these operators and all this kind of thing. So these are two very different sort of numerical tasks. This one is sort of a little bit more expensive, and here it's sometimes a little bit more tricky. I mean, you have to know what to do, but anyway, I mean, so this object we know very well. And so now I show you what the result is. I mean, so this is sort of what we see now. Of course, I mean, presumably you cannot see it so well. I mean, I guess what I want to point out is that, so this is the stretch. So we put here the full covariance, but here this is the stretch. I mean, this is the momentum, and this one is the energy. So that's sort of the low pressure in quote. And here you see actually perfect agreement. I mean, you cannot see it from the distance, but, you know, when you look hard, I mean, then you see that there's some dotted line. The dotted line is sort of a numerical simulation of the linearized generalized hydrodynamics. So this is sort of like a perfect agreement. But I thought I'd show you this because, you know, I just sort of to emphasize that it's really true, you know, at more generality. But now I look at sort of, you know, the case of sort of, you know, extremely high density, which is sort of this intermediate pressure of 0.95. I mean, that of course depends on the inverse temperature. I mean, so, you know, if I take another beta, then will be a different P. But there you can see that you know, I mean, it doesn't look, you know, not I mean, the stretch and the momentum are still sort of pretty much okay, but for the energy, this is somehow shifted above. And then why? I mean, we don't know, but, you know, we are sort of trying to understand better. But if I go to even higher pressure, then, you know, the phenomenon is that most of the weights sort of are actually sort of at the edge of our interval, and so all these peaks sort of become rather narrow, and you get an intermediate region which is sort of essentially empty. Okay, so I think that really brings me sort of to the end of this talk here. I mean, so let me just sort of summarize in one slide. I think, I mean, to me, the open, I mean, sort of let's say, open mathematical problem is a proof of generalized hydrodynamics. I mean, so for the box ball, I mean, Makiko explained us, how you can do it, and then Chiara explained it, for the hard rods. I mean, so you can see, when I learned about box ball, I mean, was immediately extremely fascinated, because box ball makes one step which before nobody could do. You see, the advantage of the hard rods is that when you look at this two-particle scattering, it's just a number, it's just the length of the hard rod, and that's it. Whereas for the box ball, it's a rather simple matrix, but nevertheless, I mean, it does depend on the particular length, particular label of the soliton I'm looking at. And so I found it interesting that we now have at least one model where you have this complication, which of course in all realistic models, I mean, that will be there, namely that the two-particle scattering lengths will depend in some way, but it will depend on the incoming velocities. I mean, that's completely unavoidable. And what would be very great if one could somehow, maybe go beyond the box ball and maybe can prove, or maybe do, somewhat more general sort of proof for GID. I mean, go beyond the box ball, or maybe more general for the box ball itself. We have somehow all the ingredients. I mean, we know what the equation of generalized hydrodynamics should look like, but it's a full dynamical sort of proof would be extremely great. Anyway, so thank you for listening.
Thank you very much. So you said that there are two different aspects of Toda case, so soliton base and particle base, and so in your list, I couldn't find any other example which really we understand both case. Is it correct?
Well, I mean, so I think if you want to have another example, which of course on which is less known, so to speak, but the next, the next example which I think one could do is the Ablovitz-Lattice. The Ablovitz-Lattice, I mean, we know already I mean, for the particle-based generalized hydrodynamics, we are sort of more or less on the same level as Toda. I mean, we know what the free energy is. I can use this argument with the symmetry of the B matrix in order to compute the average currents, and so in some sense, we are there. In this respect, we are on the same level. But since if you look in the books of Abelwitz, of course, he explains over many pages how to do the inverse scattering transform. But it was never at the center, so much at the center of attention. I mean, therefore, presumably, people were just happy by knowing that there is this inverse scattering transform, but then trying to do a step more. I mean, apparently they just didn't do that.
So okay.
So in that sense, I would think if you ask what would be the next on the list, which comes close, I mean, which has also this property, then I think it's Abelwitz-Lattice with this small point which I mentioned, which to me is still sort of a riddle. Somebody should explain to me what are the particles in the Abelwitz-Lattice model. I mean, that's somehow okay.
Yeah. So at least discrete Toda lattice should have two aspects I think for me, and but
the discrete Toda lattice.
Discrete Toda lattice has a Lux pair and also soliton solutions.
Okay, well, that would
so
be
maybe people,
another thing. I mean, my question is always. I mean, it looks to me. I mean, maybe I'm prejudiced, but it looks to me that if I have a model which has a free energy, I feel sort of a little bit more at home. But that's fine. I mean, it's just the way I'm sort of was brought up. But I mean, if you have the discrete Toda, and if you discrete Toda might be also an interesting.
So,
for the Toda soliton, hydrodynamics. I mean, you know, you have particles moving either way. I mean, that's different than in the box ball, right? But yeah, I mean, it's certainly something which one, you know, should give some thoughts and see, you know, where maybe, you know, working to the point to understand where the difficulties are.
Yeah. So my actually question was, so if we have two different aspects or two different ways, there some relation or just independent?
No, I don't think so. I think this is what I was trying to say. I mean, you know, when you look, I mean, you know, I mean, the generalized hydrodynamics comes with some condition, or you know, I mean, there are some restrictions on the initial conditions, right? And so, you know, if I look at the Toda GGE, I mean, I just cannot, you know, I mean, having an n soliton solution, I mean, looks to me like obviously a set of measures 0. You know, I mean, there's no mathematical proof, but, you know, just looking at you know, I mean, looking at this thing, it's, you know, I mean, the n soliton solution is sort of a much more constrained object, and
major 0.
It would be very surprising if this, according to the GGE, you know, would have a high probability. I mean, this doesn't look right to me. So I think what happens is that you know, you have two very distinct class of initial conditions, which you know,
independent somehow.
Yeah, that's right.
Dynamics.
No, I don't think they, you know, yeah, no, I think, you know, at step equals 0, you sort of look in sort of somewhat two different directions. I mean, only the surprising thing is that, you know, the integrable, you know, the integrability is such a strong property that, you know, eventually, you know, on the very large scale, where you have forgotten about a lot of details, you know, the hydrodynamics still has a similar structure. I mean, that of course is true. Right? But,
thank you very much. Yeah.
Yeah. Hi. Yeah, it's Benjamin. Thanks for the nice talk. So
thank you.
So similar question. So about this, the fact that they are distinct. I mean, so in my talk, I was saying, you have to look at the manifold of states and, you know, impose clustering and all that. So, I mean, are these, so supposedly you look at different type of states here. If you look at the, you know, different initial conditions, you mean different sub-manifold of states, or something like that. So, I mean, is it that, I don't know, the soliton manifold, is a subset of this particle manifold? Are the local observables that you choose different to define the state? And maybe the other question is, if you add the radiation with the soliton, do you now get the full thing, like the full?
I don't know. No, I don't know. Well, okay. I mean, you know, these are all good speculations, but I mean, my point of view is that. So let me put it this way. I mean, I think what would be, I mean, at least for myself, it would be very nice to understand better what are exactly the statistical assumptions which go into, you know, the work of Gennady, let's say.
And, there it's actually clear that the ensemble they have is certainly not it cannot describe all possible probability measures that are invariant and clustering in the KdV field.
That's right.
Because the solitons are, you restrict a lot how the fields can move around. So supposedly something like that. But if you add if you add the radiation, then supposedly you describe everything. I mean, at least in the KdV, then you would describe all possible field configuration.
Yeah, but I mean, for KdV, I mean, you don't see sort of, I mean, radiation somehow, you know, doesn't seem to appear in the hydrodynamic equations which you write down. I mean, also the one which I wrote down for the Toda. I mean, of course we know we have radiation. I mean, you know, I mean, certainly what I wrote down in this equation doesn't include it. I mean, maybe there's yet another version where you can include radiation. I mean, we don't know.
I would think it's like this initial condition. I mean, I guess if you have with the radiation, you'd have a more complete description of full manifold of states that include radiation, and then the soliton would be just a kind of boundary version of that, like a measure 0. And probably with radiation, you have the same set of states as the GGs with particles. I don't know.
Yeah, no, that's absolutely right. No. I think I think that this idea of manifold of states, I think is very useful. I mean, but on the soliton side, I mean, I mean, okay, I mean, maybe you know, simplified model like the box follow. So I mean, you might be able to identify more clearly, you know, this manifold of states. I mean, but at least sort of at the moment, yeah, I really think that you know, I mean, you look at, you know, two very different type of initial states, and I mean, and therefore, you know, a priori, there's no reason that you know, on a large scale, they should sort of look similar, right? I mean, which they just don't. I mean, you know, of course, the equation have the same structure, but you know, the actual dynamics, of course, is not the same.
Okay, are there more questions or a comment? So I just have a quick question. In your comparison between a particle and a soliton, so the last example that you have is the quantum spin chain.
Yes.
So can I think of for example, the exclusion process to be there in the XXZ chain?
No. No. I mean, you know, it should be okay. So you know, when I so yeah. Okay, the difficulty is that the word quantum, you know, is not sort of, people sort of think similar things, but not always exactly the same. So for me, quantum is that your time evolution is given by a unitary operator, which is certainly not the case for
the particle. Okay.
For you know, anything like you know, sort of stochastic particle problem. Also, you know, I mean, I guess in one of the talks, I mean, you know, they said, you know, you have the box ball, and then they sort of do sort of like a quantum version, and you know, then you have structures which are similar to integrable quantum chains. I mean, this is all very perfect, and you know, it's interesting to see that, you know, when one has these structures. But the point is, you know, in my language, this is always Euclidean. I mean, it's sort of like having the 6-vertex model. Which, you know, where the transfer matrix, of course, you know, also has a structure which is sort of similar to n-body quantum mechanics, but it's always Euclidean. I mean, there's no unitary matrix. And so if you really want to do sort of, you know, it's fine to do, you know, I mean, discrete space-time. I mean, that's just perfect. I mean, you know, many physicists study this, but the basic point is that, you know, when you go from, you know, what you call time, let's say from time t equals 0 to time 1, you know, there should be an Hilbert space and there should be a unitary operator. So, you know, just having a map like in the box ball, I mean, would not do. And then if you do this sort of what people call this, you know, quantum extension, I don't think, you know, this by itself will be give a quantum evolution. You need a unitary operator. Okay. Maybe, you know, you can put the weight sort of in a good way that it eventually becomes unitary. I mean, you know, there's a lot of work in this direction. I just want to emphasize that one basic point, that quantum mechanics, to me, if you want to study dynamics, means that, you know, the underlying object has to be unitary dynamics. On a lattice, discrete, I mean, all these things are fine. I mean, this is all accepted, but the unitarity, I mean, you should not give up.
Okay, thank you. So if there are no more questions, okay, we update in 5 minutes maybe. Thank you again.
Most welcome. Thank you.